The Dreamliner is most commonly equipped with two General Electric GEnx engines, each generating between 310 kilonewtons and 360 kilonewtons of thrust, comparable to the previous generation CF6 engines. However, the GEnx achieves this with 15% lower fuel consumption, a significant technological advancement. This leap in efficiency is primarily due to two major design innovations. The first is the engine's large bypass duct that surrounds the main engine. The primary components of modern-day jet engines are the fan, a compressor, a combustor, a turbine, and a nozzle. The ultimate goal of a jet engine is to draw in air and pressurize it as much as possible, which increases the energy potential of the air before mixing it with fuel and igniting it, causing a rapid expansion and acceleration of air. The work done by the compressor is then recovered in the turbine section, which powers both the compressor and the fan. Finally, the air, with its remaining kinetic energy, travels through the nozzle, where it is accelerated more and sent out the back of the engine to provide thrust. The engine core is the part that powers the engine. Yet, most of the air that travels through the GEnx bypasses this section completely. Instead, it passes through the fan and the bypass duct. This is one of the reasons the engine is incredibly efficient. Bypass ratios have continually increased over the years, which is one of the reasons engines keep getting bigger. The GEnx engine has a bypass ratio of 9:1, meaning that for every 10 kilograms of air that passes through the engine core, 9 kilograms flow through the bypass duct with only 1 kilogram entering the engine core. While the core takes a small volume of air and accelerates it rapidly, the fan takes a massive volume of air and accelerates it just a little, while not requiring it to be mixed with fuel and ignited. This drastically increases the fuel efficiency of the plane. The aviation industry has been aiming for engines with larger bypass ratios for decades, but there are a couple of limiting factors that have made it difficult to increase the size of the fan blades. The compressor and fan are driven by a common shaft, hence, they rotate at the same speed. But because the fan is so much larger than the compressor and turbine blades, the fan experiences much higher centrifugal forces, and if the fan blades grow too long, their tips could even break the speed of sound, leading to shockwaves and a massive increase in drag. The first problem that needed to be addressed was how to handle the large centrifugal forces. The GEnx achieved this first requirement by using lightweight carbon fiber fan blades. Older fan blades were constructed from titanium. Titanium is used for its excellent strength-to-weight ratio, but carbon fiber blades have an even higher strength-to-weight ratio, while also being much stiffer than titanium. This allows the carbon fiber composite blades to be longer and thinner than their titanium counterparts. This design allowed General Electric to reduce the blade count from 22 to 18. In all, this resulted in a 15% weight savings in the blades, allowing them to spin faster without fear of damage. However, composites do have one serious drawback: their impact resistance. One of the tests aircraft engines need to pass to get certified is the chicken gun test. This test involves shooting a dead bird into the engine and seeing how it holds up. The fan blades are the first part of the engine that any foreign object will encounter, and therefore need to be capable of withstanding the impact. Early development of composite fan blades by NASA showed that composite blades by themselves were not up to the task. To address this issue, the leading edge of the blades was reinforced with titanium alloy. The next design feature that helps the GEnx reduce fuel consumption is the extremely high compression ratio achieved through the engine's compressor section. Compression ratio is found by dividing the pressure at the exit of the compressor section by the pressure at the inlet. By increasing the pressure ratio, we can maximize the energy that can be extracted from the fuel. This is because there is more useful energy available for extraction in the turbine and nozzle at high pressure. In order to achieve higher compression and ultimately a higher pressure, there is the need to increase the number of compressor sections, but this will increase the weight of the engine, which will lead to higher fuel consumption and reduce the advantage. Higher compression will also lead to higher temperatures, which may cause material failure in the compressor blades. But most critically, increasing the temperature will result in increased emissions of potent greenhouse gases like nitrogen oxides. But how can an increased pressure ratio be achieved and at the same time meet climate change goals? This problem had to be addressed, and the engineers did it through ingenious fuel injection technology. The compressor feeds its high-pressure air into 22 fuel mixing nozzles located in a ring around the compressor exit. Their job is fairly simple: mix the fuel into the air and ignite it. The art of crafting the perfect fuel injection nozzle is incredibly complex. But with the advent of 3D printed manufacturing, GE has been able to create a fuel injector with a complex internal labyrinth of air channels that traditional tooling simply could not cut. The fuel injector they developed is called the Twin Annular Pre-Swirl Injector, or TAPS. So, how does it lower those dangerous nitrous oxide emissions? It does this by carefully controlling the air-fuel mixture ratios to control flame temperatures. This may seem like a simple device, but it took generations of design iterations with computer simulations gradually bringing the engineers closer to their target, using materials capable of resisting the enormous heat within the combustor. The 26 years of development paid off, resulting in 60% nitrous oxide emission reductions. A fuel injector compatible with a record-breaking 58:1 pressure ratio used in the GEnx. GE managed to increase the pressure ratio even though they reduced the number of compressor stages. Each of these turbine discs is one stage. The GEnx contains 10 stages, far fewer than the CF6 engine it is replacing. GE managed to do this through new improved blade design. Traditionally, compressor stages are made by attaching the blades to a separate disc with dovetail connections. This decreases manufacturing complexity, but the dovetail connection is less durable, increases assembly and maintenance costs, and allows some air to escape through the connections. Blisks are compressor stages that are manufactured from a single piece of metal, making them stronger and easier to install. The turbine also made use of new material science breakthroughs, being the first commercial engine to make use of gamma titanium aluminide, an advanced alloy of titanium and aluminium. That combines the heat resistance of titanium with aluminium's weight savings, replacing the nickel alloys of past. It took 3 decades to take this material from the lab to commercial use, and the Dreamliner was the first plane to make use of it, paving the way for the material's acceptance in the industry. All of these factors combined to allow the GEnx engines of the Dreamliner reduce fuel consumption by 15% over previous generation engines, and on top of all that, the engine is 60% quieter than similar-sized planes. Thanks in part to the engine's most distinctive feature, the saw-tooth pattern on the fan casing and the engine exhaust. These features are called engine chevrons, and they are functional parts of the engine that significantly reduce engine noise. This is said to reduce jet blast noise by as much as 30%, and allowed Boeing to use substantially less sound insulation in the fuselage walls of the aircraft, which helped to reduce aircraft weight.